Okay, so in this video we will cover chapter 2. Okay, this is the first part of the video, which is on the review of Laplace transforms. Okay, so maybe some of you have studied this before, but this chapter will review back what is Laplace transform. We'll cover on the Laplace transformation, inverse Laplace, and so on. Right. So these are some of the topics or contents that we will cover in this chapter. Look at the concept of complex frequency, one-sided and two-sided Laplace transform, and then Laplace transform of simple time function, the basic one, and then what are the theorems for Laplace transform. And then once we have performed the Laplace transformation, we will look at how to perform the inverse Laplace transform techniques, okay, from the frequency domain back to time domain. And then finally we will look at the initial value and final value theorems. So first, let's look at the concept of complex frequency. Okay. So why we use Laplace transform? Okay, so this is important, right? We need to understand why do we need to use Laplace transform in order for us to appreciate this topic. Okay, if you don't understand this topic, or if you don't understand, you don't know where we are going to use this, okay, or when we are going to use this, then how can we appreciate what is Laplace transform, right? So basically, says here our goal is to develop techniques for analyzing circuits with a wide variety of inputs and responses. So basically, the idea here is we want to analyze circuits. Okay, can either be simple R circuit, RLC circuit, and so on, right? So such circuits are modeled by differential equations. Solutions describe the total response behavior of the circuit. Okay, so in order to solve the circuit which is modeled by differential equation, which is difficult to solve, we can simplify the process or simplify the solution using Laplace transformation. Okay, so in this chapter we will review on the Laplace transform. However, in chapter 3 we will look at the Laplace transformation being applied on circuit. Okay, so in chapter 3 we will see the application. So basically, Laplace transformation involves turning, okay, changing or transform differential equations into algebraic equations. So if we can transform differential equations into algebraic equations, then we can solve algebraic equations, which is much easy to find a solution to solve the circuit, and then we inverse back into the original or the original differential equation of the circuit, right? Alright, so use Laplace transform techniques as an alternative to analyze circuits. So says here, change signals from time domain to frequency domain. So this is what Laplace transformation is about, changing the signals or the circuit from time domain to frequency domain. Then we analyze the circuit in frequency domain. Alright, and then once we have solved it, we convert it back or inverse the signals into time domain. Okay, because initially we want the solution in time domain, however difficult to solve. It is difficult to solve in time domain. We transform it in frequency domain, solve it, and then inverse it back to time domain. Right? So it says here, Laplace transform is an integral transformation of a function ft from time domain to complex frequency domain, giving fs. So initially the solution or the equation or the signals in time domain, which is represented by ft, yeah, and then when we transform it into frequency domain, right, it is now capital F S, right? S represent the frequency and T represent the time. So you can see here, if we look at time domain, right, from this angle, hopefully you can see the cursor. See how can I, right, don't mind, you can, if we look at this angle, let me try to draw something. Can I use this? Right, so if we look from this angle, we will only see this signal. Alright, so this is the signal in time domain. We see it in time domain. However, if we look it in frequency domain, which is from this angle, we will see that this single signal is actually a combination of multiple signals. Right, this is actually a combination of signal 1, signal 2, and signal 3, and so on, if there exists. So all these three combine to become this one signal. So that is the idea of looking at frequency domain. Right. Right, so basically Laplace transform can also be used to solve differential equations. So it's actually used extensively in electrical engineering, so make sure you try to understand this, because later on you're probably going to use this again. Okay, so you can see here the idea that and look at here, reduces a linear differential equation to an algebraic equation, right, which can then be solved by formal use of rules of algebra. See, this is the original circuit or the original time domain, signal in time domain. Alright, then we transform, Laplace transform. Alright, sorry, here we Laplace transform to get capital XS. Alright, and also this we can Laplace transform capital HS. Right, so these two, the product of these two is a simple multiplication of HS and XS, simple multiplication. Alright, however, if you want to multiply xt with ht, you cannot use simple multiplication, right? You have to convert it or transform it into frequency domain, then you can just do simple multiplication. Right? Okay, definition of Laplace transform and complex frequency. Laplace transform is a frequency domain approach for continuous, right? See here, Laplace transform of function ft defined for all real numbers for t above 0 is the function fs, which is unilateral transform defined by this. Alright, so here what we can take note is on the equation right? This is the equation to perform Laplace transformation, right? This is the ft, the signal ft that we want to transform into fs. So in order to do that, we need to integrate ft times exponential minus st with dt from 0 to infinity. So you can see in order to transform into fs, first you have to integrate. Alright, once you have transformed it into fs, then you can do simple multiplication or simple formal algebraic rules, right? Never mind, we will look at this in the few slides later after this. Alright, this is one example of why we convert the Laplace transform into frequency domain. Alright, so if you can see here, this is actually one simple example. Okay, so we have induction motor here. Alright, then we are measuring the current signal here, or the voltage signal, right? And then if we look, this is the signal in time domain, right? And if we look the signals in frequency domain, we will get this figure, the spectrum. So this is in frequency domain. Right, so we can see that this single signal in time domain is actually a combination of multiple signals, which is, for example, 60 Hz, and then we have let's say 60.5 Hz, and then we have 61 Hz, and then 59.3, 59 Hz. So multiple signals which are combined to give us one signal in time domain. So the good about this is, if we look at frequency domain, we can actually analyze the problem of the motor. Okay, because based on the certain frequencies can indicate the problem with the motor. So this is one example of why we use frequency domain, right? So this is in time domain. However, if we look at in frequency domain, this is the signals. Okay, remember that we look at the time domain only like this. However, if we look at frequency domain, we have so on, right? Multiple signal combined together, right?